This is how a PN junction diode would look like. The black colored part represents the P side and the gray colored part represents the N side. And now what is so special about this PN junction diode and how it could be different from a resistor? In order to understand that, you need to look at this. Look, here we are having two circuits. In the first circuit there is a resistor which is connected to a 1 volt supply, and in the second circuit there is a PN junction diode which is again connected to a 1 volt supply. Now what is a resistor? Resistor is a component which limits the value of the current in the circuit. Now the current through the resistor is in the clockwise direction. Now if you reverse the polarities of this voltage supply, now the current direction will also be reversed. Now it is in the anti-clockwise direction. This is not same with the PN junction diode. A PN junction diode is a component which allows current to flow in only one direction, and there is a current that flows through a PN junction diode when it is forward biased, and the value of the applied voltage is greater than the breakdown voltage. Now the PN junction diode is forward biased, so that's why current is flowing through a PN junction diode. Now if you change the polarities of this voltage source, now there is no current that is flowing through the PN junction diode. This is what difference between a resistor and a PN junction. Now let's start the simulation. I had arranged all the components as shown in the circuit diagram. This is a voltage source and this is a resistor of 100 ohms value. You can take any other value, no problem. This is a silicon diode and this is a voltmeter which measures the voltage across this diode, and this is an ammeter which measures the current through this diode, and this is a ground. Now here we are having two cases, forward bias, reverse bias. Now we will be discussing the forward bias. In the forward bias, the positive terminal of the voltage source is connected to the P side of the diode, and the negative terminal of the voltage source is connected to the N side. And also in the forward bias, the width of the depletion layer decreases as you go on increasing the voltage source value. Once the voltage source value crosses the breakdown value, the current through the diode increases drastically. Now if you want to know what is happening at the microscopic level, you can see the PDF which I will be attaching in the description. Go through it, you would understand what is happening at the microscopic level. And now let's start the experiment. First, we would be varying the voltage source value from 0 to 1 by increasing the voltage value by 0.1 at each observation. Now the first value is 0.1. Now the voltage across the diode is 99.995 millivolt and the current through the diode is 50.41 nano ampere. Now nothing wrong with the values, but for the plotting purposes on the graph paper, we are taking the voltage in volt and the current in milliamperes. So let's convert the millivolt to volt by multiplying it by 10 to the power of minus 3. 99.995 into 10 to the power of minus 3, which is 0.09, and the current, which is almost very small, let approximate it equal to 0. The next value, which is 0.2. Now the voltage value is 0.19 volt and the current, which is again in the nano ampere. So let's approximate it again to 0, because it becomes very difficult us to plot this value, very difficult. So we are approximating equal to 0. Now the third value, which is 0.3. Now the voltage is 0.29 and the current, look at the current value, it is 3.903 microampere. Now it has changed from the nano, so let's convert into milli, multiply it by 10 to the power of minus 3, so the value would be 0.003 milliampere the current is, and the voltage is 0.29 volt, and the fourth value 0.4 volt. Voltage across the diode is 0.39 volt and the current through the diode is 0.03. And the fifth value 0.5. Now the voltage across the diode is 0.48 and the current through the diode is 0.18 milliampere. The 0.6. voltage across the diode is 0.53 and the current through the diode is 0.61. Now here we are approximating up to 2 decimals. Now 0.7. For a silicon diode, the breakdown voltage is nearly close to 0.6 or 0.7. Once the value is crossed, the current through the diode increases very drastically for a very small change in the voltage. Look, the current is now in milliampere and the voltage is 0.57 and the current is 1.65 milliampere. 0.8. Voltage across the diode is 0.59 and the current through the diode is 2.03. Now 0.9. Voltage across the diode is 0.61 and the current through the diode is 2.86. Now at last final value 1 volt. Voltage across the diode is 0.62 and the current through the diode is 3.73. Now with this we had finished with the forward bias. Now reverse bias. In the reverse bias, the voltage source sides are flipped. That means the negative terminal of the voltage source is connected to the P side of the diode and the positive terminal of the voltage source is connected to the N side. And also the width of the depletion layer goes on increasing as you increase the value of voltage source, and here the current through the diode is only because of the minority charge carriers, not due to the majority charge carriers. And in order to know the reason, have a look at the PDF which I will be attaching in the description. Now let's start the experiment. Here during the experiment we will be changing the voltage value from 0 volt to 5 volt by increasing the voltage value by 1 volt at each observation. Now the first value is 0 volt. So the voltage across the diode is 0 volt and the current through the diode is 0 ampere. Now the second value 1 volt. Voltage across the diode is 999.999 millivolt. So let's convert it into volt by multiplying it by 10 to the power of minus 3. So the value is 0.9 volt and the current is 7.892 nano ampere. It is very small. It is because of minority charge carriers, and for the plotting purposes we need to convert this into milliamperes. For that we need to multiply it by 10 to the power of minus 6. So the value is 0.000078. 2 volt. Voltage across the diode is 2 volt and the current through the diode is 0.000088. Now I am saying the converted value in the milliampere. 3 volt. Voltage across the diode is 3 volt and the current through the diode is 0.000098. Now 4 volt. Voltage across the diode is 4 volt and the current through the diode is 0.000108 milliampere. Now 5 volt and the last value. Voltage across the diode is 5 volt and the current through the diode is 0.000118. Now with this I had completed the reverse bias. Now here we can observe that in the reverse bias the current value is very small and it is not changing at all, even though we are increasing the voltage by 1 volt. But in case of forward bias, after reaching the breakdown voltage, for a very small change in the voltage the current was increasing very large. Now this is not happening in the reverse bias. So with this I had completed the reverse bias and forward bias.